In this video I'm going to explain the concepts of converse and equivalence because they have to do with proving and disproving statements. So the converse of a statement, an implication P implies Q, is Q implies P. So in other words, we're just reversing the order there. So we need to be a bit careful because we've already got a contrapositive and a contradiction, which are terms that we use in proof. Here we're just talking about a statement. We're saying if P is true, then Q is true. The converse of that would be saying it works the other way around. So for example, we might say if n is even, then n squared is even. The converse of that would be saying if n squared is even, then n is even. Now sometimes one of the statements might be true and the converse might not be, or they might both be true, they might both be false. So note that a statement and its converse do not both have to be true, they don't both have to be false. They can both be true or both be false, or there can be one of them being true and one of them being false. But if we do have the situation where a statement and its converse are both true, then we can say that the statements are logically equivalent. So if P implies Q and Q implies P, then we can say the statement P and the statement Q are logically equivalent. So we'll think about some sort of examples of that. And if they are, so if P implies Q and Q implies P, then we can write them with that double-headed arrow. P implies Q and Q implies P. So one statement, and that indicates that P and Q are logically equivalent statements. Another way of saying that is P if and only if Q. It's a bit of a funny way of saying it, but it's kind of saying if P then Q and if Q then P. So putting if and only if between them is a sort of slightly fancy or maybe condensed way of saying those two statements. Now, to prove that two statements are equivalent, we need to prove the implication in both directions. So to prove that P and Q are equivalent, we must prove that P implies Q and that Q implies P. In other words, we must prove if P is Q, then Q. If P is true, then Q is true, and we must also prove if Q is true, then P is true. So let's think of a couple of examples, and I mean these will be relatively simple. So what about the statement x is equal to 4? We could say that that implies the statement that 3x is equal to 12. But we could also say that if 3x is equal to 12, that implies that x is equal to 4. And in fact, this is what we do all the time in algebra, isn't it? So really, we're sort of using logical equivalence all the time when we solve equations. Now, if we were proving that those were equivalent, well, it would basically just be a one-step process in each case. And in fact, we wouldn't probably even normally show working for this. But, you know, I could start with x equals 4, and then I could, multiply both sides by 3. So multiplying by 3 on both sides gives 3x equals 12. Likewise, I could start with 3x equals 12, and I could divide by 3, and I would get x equals 4. So because I can prove that statement both ways, I can say that x equals 4 and 3x equals 12 are equivalent, logically equivalent. Maybe just one more. Let's say if n was an integer, then I could say that the statement n is divisible by 5 implies that the number n must end in a 0 or a 5, mustn't it? That's true for any integer is divisible by 5, it must end in a 0 or a 5. But it's also true to say that for any integer n which ends in a 0 or a 5, it is divisible by 5. So those two statements there are logically equivalent.